Most programmers view memory as a collection of different sized segments with no particular order. The user's view of memory is not the same as the actual physical memory. Segmentation is a memory mechanism that maps the programmer's view of the actual physical memory. A programmer's view of memory consists of a logical address space, which is a collection of segments. The addresses specify each address by a segment name and offset. Usually, segments are referred by their segment number for simplicity. Virtual memory splits programs into fixed-size blocks rather than logical modules. This could work, but there are better ways of splitting programs. We can use segmentation to split programs into different size segments that reflect the programmer's logical view of memory. In this example, we use segmentation to split the program into these common segments known as the logical view of the program. This is an example of the segmentation's hardware. The CPU sends the data as a logical address, a segment name, and offset. The limit, which is the length of the segment, and the base, which is the starting point of the physical address, are stored in the segmentation table. The offset is then checked if it is less than or equal to the limit. If the offset is less than or equal to the limit, the physical address will be added to the base plus the offset and stored in physical memory. Otherwise, if the offset is greater than the limit, an addressing error will occur and a trap will be thrown.
So now that you're all segmentation pros, let me give you a quick analogy to help the information stick. As we learned, segmentation is the process where memory is allocated out in chunks called segments. This allows an application to store various parts of itself and the data that it's working on in different parts of the RAM. Imagine you have a weirdly shaped refrigerator, and this refrigerator, like most refrigerators, is subdivided into shelves that can be moved. In the same way as an application needs storage space, the operating system assigns it shelves that it can use, but these shelves do not necessarily need to be side by side. Say you're making a burger and you've just gotten home with all of your ingredients. Do they need to be stored in the same shelf for you to be able to find them? What if they don't fit on the same shelf? What if there's no room in the shelf above or below either? Can we separate your ingredients and still quickly make your burger the next day? The answer is yes, so long as we know what shelves we have and what we have on each shelf. In the same way, the OS splits up the program into logical parts and stores them in spaces in the RAM in a non-continuous order. So how do we keep track of our shelves? The OS keeps track of the segments by storing them in a segment table. The table stores a segment, the location of the start of the segment, and an offset, the distance from the start, for each segment. We need the offset because not all shelves are the same size. This is because we want to optimize our space usage. If we make all shelves the same size, all shelves need to fit our biggest item, like a gallon of milk. This limits the number of things we can store. If we're able to change the size of our segments, we can store smaller items in a smaller shelves, like egg carton in an egg carton size shelf, and a gallon of milk in a gallon of milk size shelves, thus fitting more items. And that's how you put away your groceries. How segmentation works. I hope this was helpful, and I'll see you next time.